Right now. I hope that you guys are having a good start to your day. Um, just a kind of funny thing. One of your classmates sent me a private message, and I guess it's like muscle memory. They sent me a private message, and I responded to them with, "Hey, thanks for the email." There was no email. It was a private message in Zoom. But at any rate, here we are. So last time what we were talking about was we were primarily talking about sugar structures. And when we were talking about sugar structures, we were talking about them cyclizing and what were the reactions that took place when they cyclized. If you're looking along right now, what we're looking at is week 7, day 1 sugars. That's the slide deck that we're working with. And today we're going to get through that. We're also going to go on to talk about some enzymes, and we'll probably get to some other things today. Um, Now, with that said, oh, dang, that's not what I want to do. I want to go full screen on this. Okay, full screen. Full screen. Let's try one more time. Go. And I'm going to share my screen so you guys can see kind of the slide deck that I'm looking at, and you can watch the navigation through it. Okay, so we are talking about sugars. We primarily focused on, and we worked into conversation a lot of different terminology like epimers and diastereomers. Um, there we go. Okay. So we've been looking at that D sugars versus L sugars. These are mirror images of one another. And the highest numbered chiral carbon is the carbon that's going to determine if a sugar is a D sugar or an L sugar. And just one moment, I have a 9-year-old child of mine who has a question because he is standing next to my desk. What's up, bud? Work. And so we're talking about, sorry about that. So we're talking about sugars, epimers. If you remember, did he ask about D versus L sugars? He did not. He asked about when I was going to be done, which is always the question that immediately happens whenever I start doing something. Okay. Um, so as you can see here, these two sugars on the screen, these are both D sugars. We know that because our highest numbered chiral carbon, this one right here, has a hydroxide group on the right-hand side. Now, these two sugars, they're both D sugars, but they also relate to one another. How do they relate to one another? Well, if we look at, well, we want to look at them, see what's similar and what's different. Okay, they're both aldehydes. They have an aldehyde functional group, so they're both aldoses. They both have a total of 6 carbons, so they're both hexoses. So both of these sugars are aldohexoses. Then, as I mentioned, they are both D sugars, so they're both D aldohexoses. Then what we're going to do is we're going to look at carbons 2, 3, and 4. What makes those similar? What makes those different? Carbon number 2, well, it's got in the sugar on the left has a hydroxide group on the right, as does the sugar on the right. Okay, so there's no difference there. Carbon number 3, they both have a hydroxide group on the left side, so that's identical. But then carbon number 4, that's where we have a difference. Carbon number 4 is where our sugars differentiate from one another. And since there's only differentiation at one carbon, these two sugars are known as C4 epimers because there's only a difference at one specific carbon. If you have multiple differences, then we're talking about diastereomers. Okay, these were all of the aldoses. I wanted you to know the ones that are in boxes. One of the things that I mentioned with respect to those is try to find the connection between them. What's the difference between mannose and glucose? What's the difference between glucose and galactose? Well, mannose is the C2 epimer of glucose, and galactose is the C4 epimer of glucose. Now, what's the relationship between galactose and mannose? Well, they're diastereomers. Those two sugars are not epimers of one another. The reason for that is because when you compare the structure of mannose to the structure of galactose, the differences are found at carbons number 2 and carbon number 4. So you don't say it's a C2C4 epimer because that's not the correct terminology. All right. Then we talked about ketoses and what makes them different. These were the ketoses that I want you to know about. And then we use that as our mechanism to talk about the cyclization of them. So if you remember, or one of the things that we've talked about with respect to glucose, for example, which glucose is shown on both the left and the right, is glucose has carbons 2, 3, and 4 hydroxide groups going in a down, up, down pattern. Down, up, down corresponds to right, left, right. Carbon number 1 in the cyclic form of glucose is a new chiral center, and this is known as the anomeric carbon. So that anomeric carbon is a new chiral center, and that chiral center emerges because in our cyclization reaction, which we see here, where our aldehyde reacts with an alcohol, we form a hemiacetal. Now, that OH group on carbon number 1 right here, this OH group, it can be pointed down or it can be pointed up. That is not going to change the identity or the name of this sugar. This is still going to be glucose, but that carbon number 1, whether it's down or up, is going to have a different impact on its name. I didn't mention this last class, but we'll get into it a little bit here. That hydroxide group, if it's pointed in one direction, it's going to be an alpha form of a sugar, and then if it's pointed in the opposite direction, it's going to be a beta. I'll get into identifying those a little bit later, either today or next week. Now, here's our cyclization event. Our carbonyl carbon is our partial positive charge. It reacts with a hydroxyl group. And that is how we form this ring. So our six-membered rings ring is known as a pyran ring, making a pyranose. A five-membered ring is a furan or a furanose. Now, the same sort of thing happens. The same sort of thing happens with a ketose. When they cyclize, a ketone will react with an alcohol. And whenever that reaction takes place, you still form a six-membered ring, even though your carbonyl carbon is found on carbon number 2. We form this cyclic form of the sugar. This sugar is known as a furanose. The functional group that is formed that leads to this furanose is a hemiketal. Okay, so the last thing that what we left off with at the end of last class was this right here, where we have a derivative of a sugar. We have a glycosidic linkage that forms when an anomeric carbon from a hemiacetal reacts with an alcohol, we form an acetal, and that acetal gives us a glycosidic bond. And this is important because this glycosidic bond is kind of the foundation for polysaccharides or disaccharides, basically polymers of sugars. So I'll say super important bond type in polymers of sugars. Now, sugars also can be modified to form derivatives. For instance, have you ever heard of N-acetylglucosamine? Maybe you've heard of glucosamine and chondroitin. People will take it as a dietary supplement for their legs and joints. This is an example of N-acetylglucosamine. So what that results in is we have an amination. A sugar is aminated. So let's think about this name right here. We have an amination of a sugar. So if we we have our root structure of, or we have our root name of glucose, but we have an amination. So we've added an amine at this position right here. So that's glucosamine. Now, what makes this glucosamine an acetyl, and whenever I say that in acetyl, I mean AN, acetyl, is that we added acetate. So this is an N-acetyl glucose. So this acetyl group or acetate is added to glucose with the help of an amine, which is found right here. Now, so that's basically amination of sugars is something that takes place, and those sugars provide different roles in bodies. And one of the things that they do is they provide structure for things like um, exoskeletons of insects. In addition to that, sugars can be modified where you replace basically the CH2OH with another carbonyl, and you make a glucouronic acid, galactouronic acid, manouronic acid, so you can acidify sugars. Then last but not least is we can have a reduction of a sugar. So we have oxidation of sugars, and we can have reductions of sugars. Now, if you've ever heard of sorbitol, that is an example of it's a sweetener that is not metabolized the same way as glucose. So this is I believe it's a non-caloric sweetener, sorbitol is. And sorbitol results from that aldehyde functional group being turned into an alcohol. So sorbitol is the alcohol form. I'll write this down. Alcohol form of glucose. And that alcohol group is going to be at carbon number 1. Now, the difference between these modifications, so we have basically your derivatives of sugars that are outside of the formation of polymers, is we have amination, we have oxidation, and we have reduction. So amination, amine. Oxidation, a COOH, a carboxylic acid in place of that carbon number 6. And then reduction is add an alcohol. Okay, so this right here would be a good thing to know just in terms of like, if I showed you a sugar structure and I said, what is this? Or what is this a result of? Well, if there's an amine there, it's a result of an amination. If there's a carboxylic acid or a carboxylate functional group, that's a result of an oxidation. And last but not least, if now you see something where there was an aldehyde, now there's an alcohol, that's a reduction. Could everyone give me a 1 in the chat if you followed those as good examples of derivatives? Wonderful. Okay. Now, the last thing that I'm going to cover today is to determine if a sugar is a reducing sugar. Now, sugars can be two things. They can or you can classify sugars as being reducing sugars or non-reducing sugars. And in order to kind of appreciate or acknowledge this, what you need to know a little bit about is you need to know about, well, a hemiacetal. So what I want you to be able to do whenever you look at a sugar is to identify a hemiacetal. So I'm going to go back for just a second before I proceed to this. Okay, so whenever I look at a sugar, and I see the anomeric carbon. This is my anomeric carbon. What I'm going to do, and I'm going to put a smaller dot on that. That's my anomeric carbon. What I'm going to do is I'm going to see, okay, well, there's a single bond going to an oxygen. That oxygen has another carbon single bond to it. Then the anomeric carbon also goes to an alcohol right here. It also goes to an alkyl chain and a hydrogen. Okay, I've got those four different things that it's going to. Now, to think about that, anomeric carbon goes to one, hydrogen, two, a single bond O, three, an OH, and four, a carbon chain. So that's what I'm looking for whenever I see an anomeric carbon. Now, what I want you guys to do is let's look at this structure right here, this whole sugar. Let's find that anomeric carbon. There's our anomeric carbon. What is this bound to? It's bound to a hydrogen. I'm going to circle it and I'm going to put a check mark. And then is it going to a single bonded oxygen? Well, here's that single bonded oxygen. I'm going to put a check by that. Then I'm jumping ahead because I'm going to go to, well, is it bound to a carbon chain? Yes. Now, a Y or an N. Is this anomeric carbon bound to an OH? No, it's not. You're absolutely right. Because that alcohol, that hydroxyl group, was replaced by this oxygen and this whole chain right here. So my anomeric carbon in this structure on the right is not bound to an OH. Does everyone follow that? Give me a Y or an N to the chat. Okay. Now, when you see that your anomeric carbon is, I'm going to erase my check marks. When you look at an anomeric carbon, which is what we're doing when we're looking at this one again, we're looking at this anomeric carbon. And we go through our checklist. Hydrogen, single bonded oxygen, carbon chain, OH group. When you see that you're bound to those four things, then you have what is known as a reducing sugar. And just to think back to, well, what does that mean? Or to think about, well, what does that mean? If something is a reducing thing, that means it can participate in oxidation reduction reactions. Now, what this means in terms of this sugar is that this ring can open up. So what I'm getting at there is that this right here is reversible. Now, I know that this animation shows, okay, we're linear, and then we close off and we make the ring and we're done. But what actually happens is, and I can't freeze it, but whenever it looks like this, the ring can open back up, and then this hydroxyl group can go up. It can reorient itself. So another way to think about classifying a sugar as a reducing sugar is you could classify it or think about it as a sugar that can open and close, open and close. Could you give me a Y in the chat if you follow that, or an N if you don't follow that? So another thing to think about or consider kind of like remembering is when you see your anomeric carbon, ask what it's bound to. Is it bound to a hydrogen, a single bonded oxygen, a carbon chain, and an OH? The key here is this more than maybe in anything else. Because in some instances, this hydrogen might be a C chain. Okay. And as an example of that, I want to show you the ketoses, a cyclic ketose. So this carbon right here, could you put a 2 in the chat if you can see that that carbon is our anomeric carbon? Or see how that is. And if you don't, put a W or something. And just to, I unfortunately don't have the animation for this to cyclize, but this is color coded. So this oxygen is this oxygen, which is why that carbon, number two, is our anomeric carbon. In this case, what we're looking for is, or what we really want to see is it bound to a single, is there a single bond going to an oxygen and a single bond going to an alcohol? Okay, so what we're looking for is we want to translate this structure right here to the cyclic form. This is carbon number 2. This is carbon number 1. Okay, this is carbon number 1. Then we've got the color coding of this oxygen. Okay, that oxygen is basically this oxygen. In this figure, it is the black oxygen, which becomes this OH group. This red oxygen on this alcohol is the same as this oxygen right here. So the partial positive charge of our carbonyl carbon is going to react with the partial negative charge on our OH group. And whenever that happens, this oxygen that I've got a big circle around, can everyone add a Y to the chat if you can see or recognize the big circle that I've got around that oxygen? And then does that become oxygen A or B in these figures shown below? Add your response. Is that oxygen A or B? And you have the color coding. You can use a little bit of a cheat sheet there. It's A. You're absolutely right. Okay, so this oxygen that I got the big circle around is oxygen A that I'm underlining. That means that this right here is carbon number 2. This oxygen that I'm putting I'm going to go with a square around or a rectangle, is oxygen B. Can everyone give me a Y in the chat if you see that? Great. So when we want to classify something as a reducing or a non-reducing sugar, we've got our checklist. Oh, there we are. Is it bound to a carbon chain? And I'll keep tabs on this. Checklist. Reducing, non-reducing. We look to our anomeric carbon. And we see, well, 1. Is it going to, let's go with an OH group. Carbon number 2, I'm going to put a check mark. Yes, it is. And I'm focused in on this right here. Item number 2, single bonded. Oh, draw my line. Oh, that's not a straight line. I'm going to draw straight lines to highlight these things. I'm going to erase some of these other markings. So I've got my going to an OH group. So I'm going to put a check, and then I've got my single bonded oxygen. I'm going to put a check. 3, is it going to a H or carbon chain? Yes, it is. So I'm going to put a check by that. And then my 4th criteria is it going to another C chain? Yes, it is. So I'm going to put a check by that. So this is so based on all this, how would you classify this specific sugar? R for reducing or an N for non-reducing? If it meets all these criteria, right, you're absolutely right. I put it as a reducing sugar. Now, if we move ahead, or if I replace this OH with a CH3, now my sugar is no longer reducing sugar. What that means is that that ring cannot open and close again. That ring is stuck. It's where it's in the shape that it's going to be, so it's not going to reopen again. All right. Now, so we want to know, I'm going to say, we want to look at the hemiacetal or hemiketal. We want to know, are we talking about a reducing sugar or a non-reducing sugar? So just sort of a little spoiler. I'm going to erase all these. We've got two examples of reducing sugars and one example of a non-reducing sugar. We're going to go through that checklist though. On the far left, we have ribose. I'm going to draw in my hydrogens so I can keep tabs on it. And I'm going to go with my checklist of H or C chain, a C chain. My third item is single bond O. And then my last is going to be a two C chains. Uh, Single bond O. Um, yeah, my last is an OH group. Okay, so these are my criteria. And I'll just put 1, 2, 3, 4. Okay, so my anomeric carbon. First, is it bound to a hydrogen or a carbon chain? Yeah, right here. So I'm going to put a check by that. Next, is it going to a carbon chain? Here's a carbon chain. So I'm going to put a check by that. Next is there a single bonded oxygen? Yeah, there is. Put a check there. And then number 4 is, does this have an OH group bound to it? It does. So I'm going to say check. So that ring can open and it can close. Next up is lactose. Okay. We've actually got 2 anomeric carbons. Okay, so our next sugar, lactose. I'm going to use my 1, 2, 3, and 4. And we're going to go through this checklist for both of my anomeric carbons, and then we'll revisit 1, 2, 3, 4. Okay, so this anomeric carbon first. I'm going to put this one, I'm going to color code it. I'm going to go with, let's go with a light blue. Talking about this anomeric carbon. First question, does it go to a carbon chain? Yeah, it does. Oh, and I got to draw my... A hydrogen or a carbon chain? Yes, it does. Next up, does it go to a carbon chain? Yes, it does. So I'm going to put a check mark by number 2. Number 3 is, am I going to a single bonded oxygen? Yes, I am. Number 4, does this anomeric carbon go to an OH group? No. Does everyone follow my 1 through 4 checklist for the blue anomeric carbon? Add a Y or an N to the chat. If your answer is N, let me know at what point which number do you not see? Okay, now I'm going to go on to my other anomeric carbon. Again, if you didn't see it, then does two oxygens, does two O matter? Does 2O matter? I'm I presume what you mean is this for number three. Okay, great question. Um, it does, but what we're most interested in there is not so much, just a second. Yeah.
Do you know where my iPad is?
The dog crates.
That is so bad placement with them.
Okay, so does we have two single bonded oxygens? It does matter. We only want one single bonded oxygen. Um, and so if we have two of them, that means we're probably sacrificing something else. And in this case, with this particular one, we are. We're not going to an OH group. Instead, we have another single bonded oxygen. Does that make sense? Okay, great. All right, so now we're going to our other anomeric carbon. Question number one. Do we have an H or a C chain? We do. We have an H right here. So I'm going to put by one check mark. Get your feet out of there, buddy.
I can't.
I'm sorry. Okay, so we have a carbon-hydrogen bond, which I've got at number one, check. Then, are we going to a carbon chain? Yes, we are, right there. Check. Number three, do we have a single bonded oxygen? Yes, we do. Check. Number four, do we have an OH group? Check, we do. Okay, I guess my criteria for three and four, I'm sorry if they're a little bit confusing. The single bonded oxygen cannot be an alcohol, cannot be a hydroxide group. I'll say non-OH. Does everyone follow the evaluation for both of our anomeric carbons there? Add a Y or an N to the chat if you follow all that. Okay. Now, this is class. So what that means is that I need you to answer. I just circled a carbon, one of my anomeric carbons in green. Could you tell me, is that an anomeric, or sorry, could you tell me if that is a reducing or a non-reducing sugar? Add R for N. Perfect. It's a non-reducing sugar or a non-reducing component. Now, this one right here that I've added another circle in green. How would you classify that? Reducing or non-reducing? Reducing. Perfect. So what that means ultimately is that if you have this lactose, which is a disaccharide, if you have two sugars that make a polymer, does everyone see how that's two sugars that make a polymer? Add a Y or an N to the chat. Okay. Whenever you look at that, okay, I've got two sugars that make up this polymer, this dimer. Is there a reducing end? Can everyone see how this is a reducing end? Y or N to the chat. If there is a reducing end, that means this is a reducing sugar. So it doesn't matter if you have, two non-reduce, if you have more anomeric carbons that are non-reducing, as long as you have one that is reducing, that is classified as a reducing sugar. Now we're going to go on to our last molecule, and this is sucrose. Sucrose is a non-reducing sugar. Why? Well, if we look at this, here are both of our anomeric carbons. Anomeric carbon right here. Let's go into hydrogen. And for both of these, our criteria are questions 1, 2, 3, and 4. will be answered basically in the exact same way. Question number one, are we going to a hydrogen or a carbon chain? Here is going to a hydrogen, here is going to a carbon chain. So for both of those anomeric carbons, the answer is yes. So I put a check mark by them. If you follow that, put a 9. If you don't follow that, put a 4 in the chat. Okay. So now I'm going to go on to my second criteria. My second criteria is, does this anomeric carbon have a carbon chain that it is bound to? There's one, and there's one. So that would be a check. My third item is, well, do each of these anomeric carbons have a single bonded oxygen that is not an OH group? Yeah, right here, but also you can make the case right here, right here. Okay, so before I get ahead of myself and mark those up and start analyzing that, I want to see if my fourth criteria is met. My fourth criteria being, is this anomeric carbon bound to an OH group? Well, is this an OH group? Add a Y or an N to the chat. Then follow up to that, is this an OH group? No. So question number 4, for both of them, there is no OH group that my anomeric carbon is bound to. Could everyone give me a 7 in the chat if, okay, that makes sense. I know how to analyze and look for a reducing end of a sugar, or a Q if, wait, that doesn't make sense. Okay, great. So what I'm going to do now, that kind of wraps up what we're talking about with respect to sugars. We will get more into the structures of sugars after we talk about enzymes here. I'm going to change my share because now what we're going to do is we're going to be revisiting enzymes. So we're changing paces a little bit and we're kind of pivoting, but we're going to be revisiting how enzymes work. So if you remember, when we talk about enzymes, actually, could anyone add to the chat, what's an enzyme typically made up of for our purposes in class? What are enzymes made up of? Enzymes are typically proteins, and proteins are made up of amino acids. Perfect. So what we're going to be getting into in this segment of class is, well, how do those different things work? How do those amino acids work to carry out a function? How do they act as the biological agents of change? Now, if you remember, one of the things that we talked about with respect to enzymes was we looked at a curve. We looked at that activity curve known as a Michaelis-Menten plot. The Michaelis-Menten plot looked like this. On our y-axis, we had V sub 0. Does anyone remember what the x-axis was looking at? The x-axis was substrate concentration. Okay. Now, I want you to tell me, I'm going to give you 3 different answer options, A, B, and C. Which one of these curves that I'm about to draw was the one that we saw that most resembled an enzyme activity curve? We got C, then I'm not good at drawing. Was it A, B, or C? I'm drawing the letter corresponds to the line that they're closest to. The C, absolutely. So C was where our enzyme kind of hit its highest rate. And what we saw was a gradual increase and then it kind of plateaued. Now, if we call this, what do we call this basically? Add to the chat what that was known as. If our y-axis is our enzyme's velocity, that was our Vmax. Perfect. Okay. Now, the other variable that we looked at was we looked at what substrate concentration we needed. What this right here did we need to get to half of our maximum velocity? And that is known as our Km. So in order to like plot this, what you would do is you'd say, okay, well, this is my Vmax. Okay. I'm going to eyeball it and um, I'm going to go ahead and say that this right here is approximately half of my Vmax. Add a Y or an N to the chat if you'd agree with that. Okay. So it's like I'm playing a game of Battleship where I identified one coordinate. My other coordinate is going to be my substrate concentration. So dot, dot, dot. This right here is going to be my Km. Give me a Y or an N to the chat if, okay, yeah, I see that. And I'm familiar with that. Okay. Now, Km does a couple of things. It gives you an idea of how much does your enzyme want to bind to a substrate. Now, this, so give me an L in the chat if the data in this plot right here, is it linear or not linear? And I struggled with this term for the longest time. L for linear, N for nonlinear, because I was like, wait a minute, L? That sounds like line. Yeah, absolutely. This is not a straight line. So this is nonlinear data. Now, from your experience, is it more fun to plot or easier? I'm going to say easy is the same as fun in this case. Um, is it more fun or easier to plot linear or nonlinear data and kind of expect trends? Yeah, it's more fun and easier to plot linear data. Now, when you have a graph like this, you can convert this into what is known as a Lineweaver-Burke plot. That's where we take the content or the data that makes up the y-axis and we calculate the reciprocal of that. So we would take this and come up with a 1 over velocity. That is the reciprocal of that. So all of the data that come here, so let's say it's 0.1, 0.2, you would say 1 divided by 0.2, and that would give you the points for your y-axis. Does that make sense? Add a Y or an N to the chat. Okay. Then you do the same thing for the substrate concentration. And you would plot, well, 1 over substrate concentration. So this is commonly called a Lineweaver-Burke plot, but people like to save time and they like to call it a double reciprocal plot. Now, give me a 7 in the chat if that makes sense, or a 3 in the chat if where did the double come from? Where did the reciprocal come from? Okay. So what that means is this double reciprocal plot, also known as a Lineweaver-Burke plot, is a friendly way to linearize Michaelis-Menten data, or linearize a Michaelis-Menten plot. Give me a Y in the chat if that makes sense, or an N if that does not make any sense. Now, great. The way that that shakes out is you take this graph data, you calculate the reciprocal values, and you end up with something that looks like this. Then you have a nice trend line that looks like this. Could anyone make an approximation as to what the equation for this line is? Or heck, the equation for any line? Y equals mx plus b. Great. Now, a fair question and an important question is, well, how does that help me with my Vmax and my Km? Because those are those super important parameters, aren't they? Well, the way that that helps is when you calculate the Km with this Michaelis-Menten plot, you're making an approximation. Same thing goes with the Vmax. You're making an estimation. And you're just kind of eyeballing it almost and saying, well, this is where it plateaus. That's probably our Vmax. Whereas when you linearize it, your x-intercept right here is the same thing as, your x-intercept is equal to negative 1 over km. Your y-intercept is the same thing as 1 over Vmax. Okay. Now, let's go ahead and, if I were to give you this plot and I said, hey, this number right here is 3. Your y-intercept is 3. Can you calculate your Vmax based on that? Go ahead. Whenever you do that, go ahead and plug it into the chat. Your y-intercept equals 3 is equal to, or that value solve for Vmax and plug it into the chat. One over 3. Now I see a negative 1 over 3. Well, remember we're talking about the y-intercept, this point right here. That's a positive value. That's 3. So 3 y-intercept is equal to 1 over Vmax. Then you just do the algebra, and you end up with Vmax equals 1 over 3, which is the same as 0.3. Does everyone follow that? Add a y or an n to the chat. Okay. Now, if I said your x-intercept is equal to negative 5, solve for Km. Solve for your Km and tell me what that is in the chat. Okay, I see a negative there. I told you that your x-intercept is negative 5, and your x-intercept is equal to negative 1 over Km. So in this case, our negatives cancel out. So negative 5 equals negative 1 over Km. Negatives canceling and erase those. Effectively, Km is equal to 1 over 5. Absolutely. So our Km equals 0.2. Could everyone add a y or an n to the chat if that makes sense? Okay. Now, understanding this Lineweaver-Burk plot, this double reciprocal plot, is super important. I'm going to, just a second. I'm going to give us another slide to work with real quick. So here's our, I'm going to give you 2 different enzymes. I'm going to just put together 2 different plots There's one enzyme, E1, and then I'm going to switch colors. E2. Okay. Then we'll go 1, 2, 3, 4, 5. 1, 2. So -1, -2, -3, -4, -5. 1, actually, I'll go 0.1, 0.2, 0.3, 0.4, 0.5. Can everyone confirm that they follow those numbers and are good to go with a Y in the chat? Okay. Now, with that, what I want to do is I want everyone to take a moment and try to calculate for E1 and E2, calculate your Km and your Vmax for these two different enzymes. And I'm going to do it alongside you. So what I'm going to start with is, what is my Km for E1? -1 is equal to, that's my x-intercept, that's equal to -1 over Km. So for E1, I would end up with Km equals 1 over 1 because the negatives cancel out. So E1 has a Km of 1. Now, using E1 again, I'm going to calculate the Vmax. My y-intercept is 0.3. That is equal to 1 over Vmax. So Vmax, do the algebra to rearrange this. It's 1 over 0.3, which is the same as approximately, I'm just going to do some rounding. I'm going to call it 3, as opposed to 3.33 and so on. Now I'm going to switch over and I'm going to talk about enzyme 2. Okay, E2. Okay, my y-intercept is 0.5. That's equal to 1 over Vmax. Vmax is equal to 1 over 0.5. So this is for E2 right here in red. And 1 over 0.5 is the same as 2. Then I've got my E2. I'm calculating the Km. -5 is equal to -1 over Km. So Km is equal to 1 over 5 or 0.2. Could you give me a 7 in the chat if you followed that and you did the same thing, you got the same numbers, or a letter N in the chat if you did something different and got different numbers? Okay. Now, the first thing that I want to ask you guys is, which one of these enzymes was faster? Which one of them catalyzed the reaction at a faster rate? E1 or E2? E1. Okay. Now, between E1 and E2, which one of these enzymes was able to bind to its substrate with a greater affinity? E1 or E2? E2. With a lower Km, it bound to its substrate with a greater affinity. Okay. Being able to do this is really important. Being able to process information, see these differences, see these similarities, I think is helpful. This, or not, I think is helpful. This is essential. Now, one of the things that I know people always struggle with this is they see a graph like this and they say, oh, well, I know how to do this. It's a double reciprocal plot. And then they skip steps and they do things like, oh, well, our Vmax right here is 0.5. Done. Got it. Save yourself the stress and the struggle by spending the time to do the calculations for this. Okay. Now, the next thing is these are both reciprocal axes. So you should expect, okay, well, if this from this point right here to this point right here, what did my Km do? If it shifted from here to here, well, my Km went down. It went from 1 to 0.2. And so spend the time to do that. All right. So Km gives you a sense of how much does an enzyme want to bind to a substrate, and your Vmax is how quickly can a reaction be catalyzed. The double reciprocal plot sums that up very well and very easily, as opposed to the Michaelis-Menten plot. Now I'm going to go back to this slide because I'm going to clear all of this, and I'm going to go up here. Km, in addition to just being the way that I always summarize it is Km is really just a measure of affinity. The lower the number is, the more that your enzyme wants to bind the substrate. In addition to that, it's a ratio of rate constants. So it's considering the forward reaction and the reverse reaction. And so you might see Km listed as such. You have your forward reaction rates and your reverse reaction rates considered. Now, what that means ultimately is, remember you have your free enzyme and your substrate. The binding of that will give way to this ES complex. Okay, so K sub 1 is your forward reaction rate. Basically, the question is the formation of that enzyme substrate. And then K2 is you're going on to make the product. And so that K2 is grouped with the K sub minus 1, or that K minus 1. K1, sorry, K minus 1 and K2, what are they both doing? They are both going towards the breakdown of this enzyme substrate complex. So we have a ratio of, well, the rates that make ES and the rates that, well, or sorry, that not make, that break ES and those that make ES. Now, a fair question to ask is, well, isn't there a K sub minus 2? There is, but it is such a negligible rate that we kind of don't even concern ourselves with it. Okay, so what I want you guys to know about Km is that it's a measure of affinity. And I think that's the most straightforward way of looking at it. Now, Km can be equated to a dissociation constant because a small Km means very tight binding and a high Km means very weak binding. If you're looking at this ratio of breaking up ES or making ES, well, the smaller that Km is, the more that you're going to be making that ES. Now, how can you use Km? Well, it's useful when you compare Km for different substrates for one enzyme. For example, hexokinase. This is an enzyme found in glycolysis, the process of breaking down sugars, and this will bind to two different substrates, ATP and glucose. And what hexokinase is going to do whenever it binds both of those, it's going to transfer a phosphate group from ATP onto glucose. Now, between these two, label it A for ATP or D for glucose. Which one of these does hexokinase have a greater affinity for, A or D? D. Absolutely right. The smaller the Km, the greater the affinity. Now, in addition to that, well, let's think about this. This name, hexokinase. Hexokinase, what it loves to do is it loves to get glucose. That's kind of your ideal, like if you go to the hospital, they'll put you on a glucose drip in the event that you can't eat so that your body continues to get energy and fuel sources, or a good fuel source. Well, what if you eat fructose? What if you consume fructose? Well, hexokinase will bind that, but Is it going to bind? What does it have a preference for? Glucose or fructose? Between the two, if you gave if you gave hexokinase an equal amount of glucose and an equal amount of fructose, it's going to go after the glucose and deplete that before it starts working on that fructose. So its preference is to get glucose as opposed to fructose. Now, does that make sense? Add a Y or an N to the chat. Great. So which of these sugars binds more tightly? Well, it's going to bind that glucose. Now, if both sugars were provided with an equal concentration of 5 millimolar, which of these two sugars would the enzyme be operating at its maximum velocity? Okay, now this is kind of a tricky question. This is a challenging sort of question. Okay, if you gave them each 5 millimolar, okay, which of them would it be operating at maximum velocity? Or which one would, the way that I always kind of visualize this is here's my plot, here's my Michaelis-Menten plot, here's my half of maximum velocity. This is the plot for glucose, 0.05. If I doubled that concentration to 0.1, chances are I'm going to be like right here. Is that Vmax? Not quite, but it's higher. Consider 5 millimolar versus 0.05 millimolar. This concentration of glucose that you're providing your enzyme with is like 100x larger. Does that make sense? Add a Y or an N to the chat. Okay. Whereas fructose, 4x. Multiply the concentration of fructose by 4, that will get you to 6 millimolar, which is pretty close to the 5 millimolar. So you're really not that much higher. Okay. Now, hexokinase and glucokinase are two enzymes. Which one of these enzymes has a higher affinity for glucose? H for hexokinase or G for glucokinase? H. Absolutely. If you can compare those two things, you're going to be in a good place with this. Now, which one of these is more than likely? And I would phrase this question more than as a more than likely going. What was the question? Okay, so this question right here, if both of the enzymes were at, or if both of the sugars were at 5 millimolar, which one would more likely be at Vmax? We're looking at the one that has the higher, or the higher, sorry, basically the one that has the lower affinity, no, the higher affinity, and therefore our glucose is the correct answer here. Because that's going to get us closer to because that concentration is so much higher than fructose compared to its Km. Which enzyme is operating at Vmax when glucose is at 4 millimolar? Let's take a break and look at this. Okay. If glucokinase has a Km of 20 millimolar, what concentration, and add to the chat, what concentration of glucose will get glucokinase to half of its maximum velocity? Add it to the chat. Glucokinase has a Km for glucose of 20 millimolar. What that means is that glucokinase needs 20 millimolar to catalyze at half max speed. Add a wire and into the chat if that makes sense. Okay. Now I'm going to ask you a couple of questions. If you give glucokinase 6 millimolar glucose, will it be at half of max speed? Wire it into the chat. 8 millimolar. 12 millimolar. 4 millimolar. 20 millimolar. 19 millimolar. Okay, so if you give it 20 millimolar glucose, then it's able to catalyze the reaction at half of its max speed. If you give it more than that, it's going to be able to go a little bit faster than half of its max speed. So you could almost think about this as, well, yeah, if you go to 21 millimolar, how fast is the reaction going? Oh, it's like 0.52, a little bit more than half of max speed. Does that make sense? Add a wire and enter the chat. I always think about KM as almost like a salary. Glucokinase says, listen, if you want me to catalyze this reaction, you got to give me 20 millimolar of glucose. And then I'll go half as fast as I can possibly go. You're going to give me 4 millimolar? I'm not even getting out of bed for that. Will I do the reaction? Yeah, slowly. You give me 20 millimolar? Okay, cool. I'm going half as fast as I can possibly go. I'm not getting close to my maximum velocity. I'm going half that fast. Okay, does that make sense? Wire into the chat, please. Okay. So Km, Vmax, these are things that are important to know to be able to visualize, understand how we can get there. And the next variable that I want you to be familiar with is Kcat. This is your turnover number. Your turnover number is the measure of catalytic activity. Okay, that seems kind of redundant. Well, when an enzyme is saturated with a substrate, the observed rate constant is known as the Kcat, or the turnover number. The turnover number is the number of substrate molecules converted to product per enzyme active site. Okay, this blows up an important point. One enzyme might have 5 active sites, 5 AS, we'll say. So it's almost like an enzyme is if you think about an enzyme, it's not as like a factory. It might have 10 different conveyor belts or assembly lines, whatever you want to say. There are some enzymes, one enzyme, one assembly line. There are other enzymes that have 10 different assembly lines where they can make that product. Now, this is our turnover number takes that into account. The number of substrate molecules converted to product per enzyme active site per unit of time. So what we do in order to calculate that is we say Kcat is equal to Vmax divided by our E sub T, which is our enzyme at a given time. Now, when we think about a Kcat, we arguably want a very high number. Okay, so the higher the number is, that means basically the better that each individual active site is. I've always kind of thought about a turnover number as how good is an active site, or is each active site, I'll say. Okay. Now we can take that Kcat value and think about catalytic efficiency. So Kcat is a measure of, well, how fast did the enzyme do it? Or what is our maximum velocity versus our enzyme concentration? Catalytic efficiency is, okay, well, how fast can that be done? But what is our affinity for our substrate? And is it a very high affinity, low affinity, and so on? Under physiological conditions, our substrate concentration is not saturating, or our saturation or our substrate concentration is less than our Km. This estimates how perfect an enzyme or how efficient an enzyme is. A ratio of Kcat over Km is an apparent second order rate constant. It measures how the enzyme performs when substrate concentration is low. The upper limit for this is the diffusion limit. Now, when it comes to doing this sort of calculation and looking at our Kcat over Km, we want a high number. So the way that I want you to think about this is, okay, this is the last thing that we're going to talk about, and I'm hopeful that I can sum this up well for you. I'm going to give myself a new slide and put some example content in on that. Okay. So here what we have, let's look at two different enzymes, E1 and E2. I'm going to give you a couple of different parameters about these two different enzymes. And we're going to basically ask the question, which of these two enzymes is better? E1, we've got a Vmax. I like to use simple or simpler numbers. So let's say our Vmax for E1 is 10 and our Vmax for E2 is 5. I don't want you to stress about the units. Just think about them as, okay, well, that's what I've got. 10 is just sort of our arbitrary number, 10 products per second. Okay. So that's our maximum velocity. Then I'm going to give you a Km. And so I think everyone would look at this and they'd say, okay, our Vmax, E1 is better. E1 produces more per second, or it has a maximum ability, faster top speed. Km. Let's say that our Km for enzyme number one is 0.5, and then enzyme number two is, let's say that it's 3. Okay, so if you're looking at the Km, I think it's pretty reasonable to say, okay, well, our Km for enzyme number one, well, let's say it has a higher affinity for our substrate. So a Y or N to the chat, do you follow that? We kind of confirm E1 is good based on these two metrics. Or we'd agree that these two are a Y or N to the chat. Okay, great. Now, let's say I'm going to come up with active sites. Let's say that enzyme number one has 4 active sites, and enzyme number two has 1 active site. Now, thinking about these numbers, what that active site number is going to do is that is effectively this number right here. So that's effectively our enzyme concentration at a given time. So I'm going to say E T. Now, I want you to think about this as, well, how does that reframe the other numbers that we've looked at? Okay. Essentially what that means is that enzyme number one has to have 4 of these assembly lines running in order to reach a Vmax of 10. Does everyone follow that? Y or N to the chat? Okay. Meanwhile, enzyme number 2, well, it has 1 assembly line going, and it makes 5 per second. So if you were to compare E1 and E2 in the context of this, what ultimately is our Kcat, which are Kcat is equal to Vmax over ET. We want a large number to look at and to think about our KCAT. Which of these two enzymes is better, E1 or E2, with respect to our KCAT? And the way that I kind of want you to think about this is which of these enzymes, one or two, does more with less? E2 has one active site, so it has one assembly line making a maximum of 5 per second, whereas E1 requires four active sites. So what's your vote? E1 or E2 is going to have the higher KCAT and therefore is the better one. Great. So this would be 2.5. This would be 5. So if we compare Vmax and Km, and I'm going to switch colors. I'm going to use an orange star, 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 but then our KCAT, E2 would be better. Now, I think a fair question is, yeah, but what's the metric that we really care about? The metric that we're going to care about is our KCAT over Km. That's a ratio of our KCAT compared to like what's doing more with less, but which of them is going to be able to bind the substrate with greater affinity? Because what we want our enzyme to do is bind the substrate, turn it into a product, release it. Does everyone follow this table so far? Add a Y or an N to the chat. And if you're putting an N, if you follow up and tell me why, it's super helpful. Okay. So I'm going to put this in. I'm going to say 2.5 divided by 0.5. Then I'm going to say 5 divided by 3. 2.5 divided by 0.5 is 5. 5 divided by 3 is 1.7. Okay. Yes, this is just a ratio, but what we're looking for is a higher number because that means that we're going to be able to use those substrates and produce products. When we look at these two values, KCAT over Km, which is our kind of preferred enzyme, E1 or E2? The higher number, the higher ratio is going to be the KCAT over Km that we want. Because we're going to be able to bind it, we're going to be able to produce a product, and we're going to move on. So E1 kind of wins with respect to KCAT over Km. A fair question is, well, why? Well, ultimately, the lack of affinity that E2 has for our substrate. Now, if this were something like, if this were 1, that'd be a different story. They would be equally efficient enzymes, but this was 3. Now, could everyone give me a Y or an N to the chat if you follow all that? Okay. I'm going to wrap it there. I'm going to I'm going to stop my recording.